Welcome back, ladies and gentlemen. So this is the first case, and I wanted to close some loose ends on the idea of electric potentials and potential energy before we move into some new material. In the last couple of videos, we learned about all the theory behind it, but we also did some problem solving. And so today, I really just want to tie up some loose ends that we didn't really talk about, because one of the things where this is ultimately going is we realized the big key word in going from potential energy to potential was this idea of voltage, right? And we're familiar with voltage in our everyday life in terms of batteries. So clearly this is going to lead us down the road of an electric potential will be able to, is related to an electric field. An electric field is related to a force, and a force is something that can give an acceleration or move charges. And so that's how we follow this line of, this train of thought down. And again, since potential is related to potential energy, since you have some energy stored, kind of like a battery, it creates a potential, a difference, a potential difference between two terminals, right? The positive terminal and the negative terminal, right? And when you connect something to it, it allows for something to flow, it allows for something to happen. So we can't make that jump into the idea of electricity or currents or circuits or the flow of these things, the flow of charge, until we really just pin down some really fine points about how potential is related to electric field and what that means for us going forward, okay? So that's the entire purpose of this video, is to talk about those little relationships that are gonna pop up and become super important. And then we'll work through one or two very brief problems in that same vein. And then with the next video, we'll start talking about our first application of something, our first material application of, you know, when you have a potential difference with some charge on it, what are some other properties that it causes to arise? And the first one of those will be this idea of capacitance, okay? So let's jump straight through it. Okay, so how does an electric field relate to potential difference, right? So remember, right, the formula for electric field, right, if we're just talking about a magnitude of an electric field, looks something like this, and the formula for potential looks very similar. Again, if we're talking about a single source, single point charge potential, they look very similar. We could see the only real difference is that one of them is multiplied by a distance, right? If r is the distance between two objects from center to center, we really see that if we multiplied E by another r, then we'd be left with the potential, right? So that's important for us to keep in mind, okay? That relationship-wise, they look like a similar formula, but they are different. And remember that this one is always a vector, and this one is always a scalar. Two big important things there, okay? But since we know that potential difference is something that we know how to measure very regularly, voltage, right? A voltmeter. Many of you have probably used a voltmeter at some point in your life to test the terminals of a battery, whether it's your car battery or a battery that you have lying around the house, and see if there's, you know, the potential for energy to flow. No pun intended there, right? But a voltmeter is something that's very, very common, okay? And so we can use the idea of a volt or a potential to figure out information about an electric field. So let's talk about some relations between them. So let's say that you have the ability to measure potential, okay? And let's say that, you know, we had some surface that we're measuring potential on. And let's say I put my voltmeter on the surface and I get a certain potential here, let's say 10 volts. And then I put my voltmeter over here, and let's say that it's increasing to 15 volts. And let's say, you know, it's increasing linearly again to 20 volts, okay? Where these are separated by some distance, D. We'll say that that D is the same in both of these. That's irrelevant for this discussion, right? But again, we know that there's going to be a relationship between the potential difference here and the electric field, okay? So first and foremost, okay, is that if we can measure a potential difference, right? And by potential difference, we just mean a place where you have a potential of one thing, then a potential of another. It doesn't matter if it's positive or negative, okay? But if we can measure a potential difference, we know there's got to be an electric field there, okay? In fact, it's beyond the scope of this class because we would need some calculus to explain the directionality here. But there is a property that says, number one, the direction of electric field always points in the direction of decreasing potential. Now, to get the real reason for this, we need some calculus, but you can get a good, reasonable reason for this, right? If you have some potential difference, right, it means that you have some difference, some net charge Q at one end and some net charge of the negative Q at the other end, right? And we know that the way the charge flows, okay? So that tells us that the E field here is going to be going like this, right? The electric field points in the direction to the lower potential, okay? The other thing is, notice how I drew it, okay? And this is another piece that, again, to get the real directionality, you really need calculus, right? But the direction is also always perpendicular to equipotential lines. So if we said that everywhere along these black lines here, that voltage was 20 volts, and everywhere along this line here, this voltage was 15 volts, then the electric field is first and foremost going to always be flowing in the direction towards the lower potential, and the direction is always going to be completely perpendicular to the place that you have an equal potential. If we made some other measurement and it was wonky at some other direction, right, that these were the equal potential lines, here's some VA and here's some VB, right? Again, let's assume now that VA is less than VB, right? Then we can see that the potential field lines for this case, or the electric field lines, again, are going to be perpendicular, right? Perpendicular, that becomes a right angle, and in the direction of decreasing potential. Okay, so no matter how we draw this, if we follow these two rules, we'll see how the relationship between electric field and potential goes. There's also ways that we can attack this mathematically, okay? Again, the low-hanging fruit, right, is kind of sitting right in front of us up here, right? That if we multiplied, right, like I said before, if we took this and we multiplied E times R, right, we would see that this would be, oops, excuse me, this would be equal to V, right? So that's really going to be what we're hunting for here. But notice the small difference, right? We've been talking about this in terms of a potential difference, right? Where you have some potential at point A, some potential at point B, and there is some difference there, right? So let's make sure that we can get that correctly. Let's go back to last semester and talk about the concept of work, right? We know that work is a force dotted into a distance, right? Technically speaking, the way that we drew it last semester was with X representing a distance, right? And remember, the dot product said you must be in alignment. The force must be in alignment with the distance that you move, right? So you select out, excuse me, the components that are there, okay? For this easy case, let's assume that the force is directly in line with the distance that you want to move. What am I really saying? Let's say that you have an electric field, right? Let's say that you have an electric field. It goes something like this, right? And you have 2 points A and 2 points B, right? And you want to apply some work to move a particle from B to A or from A to B, whatever the case may be, depending on the charge. Then we know that the relationship between the force and the electric field, right? I remind you that force is equal to E times the charge that we want to move, we want to do work to. So this would be E times Q times X, right? The distance that we actually want to move, okay? And what's nice about this, we know that this is equal to the negative change in potential energy last semester, right? Where you start, where you end up minus where you start, the negative of that whole thing. Okay, well, remember though, that potential is, potential energy is related to potential by being this charge that's in question here, multiplied by V. And so what we see is then, is that this is negative Q delta V. So let's take this side and set it equal to this side. And we see that it doesn't matter what charge that we're actually talking about, because that charge is going to cancel, right? And so what we get is electric field times a distance is equal to the negative change in potential. Now, remember, this is based on last semester when we defined the change in potential as V final minus V initial. So we can now just say that E times X is really V initial minus V final if we take that negative into account. So if we don't care about which place is initial and which place is final, if we only care about the magnitude of this, right, then we get left with this formula right here, which, by the way, we said was going to match our gut check between these two, right? E times a distance is equal to a potential. E times a distance is equal to the change in potential between those 2 points. It's saying the same thing, and we got to it two different conceptual ways, okay? So this is going to be really important for us, and we can actually use this with these two rules that we discussed over here to do some really simple problem solving, okay? This is meant to be kind of the downswing of this topic, right? Really just applying this, or the hope to use this, like I said in the beginning of this video, we're really hoping to use this to apply to basics, or the idea of basics of circuits and circuit elements, which will be coming up later on. So I want to do this problem right here. What are the magnitude and direction of the electric field at the dot in that figure? So take a look at this figure and what we have here, right? We have some lines of equipotential in green, kind of just like how we talked about a minute ago, separated by some difference. They're increasing that every 1 meter that you go, every 1 centimeter that you go, you're changing the voltage by 100 volts, right? You're applying your voltmeter, and everywhere along that first green line, you get 0. Everywhere along the second green line, you get 100 with a 1 centimeter separation distance between the two. Just by knowing that, and just by knowing the rules that we talked about with that voltmeter, we can figure out the electric field. Again, what's the benefit there? Figuring out electric field tells you the force. Force is Newton's laws, and so Newton's laws tells us everything that we need to know. Okay, so what is the magnitude and the direction of the electric field at that dot? So how can we first get the direction? We know that it's going to be perpendicular to the equipotential field lines, and we know it's going to be cascading down in the direction of decreasing field. So doing it in red, just like we did before, right, we can see that, yeah, this is definitely going to be the perpendicular piece. Now, which way do we put the arrow? 200 goes down to 100, so it is definitely, the electric field is to the left, okay? So the direction right away then is to the left, which, by the way, if you're putting that into something like your homework system, you know then that means 180 degrees, okay? How do we get the magnitude? Well, remember that we already said that E times D, some distance D, is equal to the change in potential, okay? Here, if we want the electric field, we can solve this for the electric field, and we see that the electric field is going to be the change in potential divided by the distance at which that change occurs. Here we see a distance, 1 centimeter, and we see a change in voltage, 200 to 100. Again, 1 centimeter though, very, very bad unit. That has to be converted to meters. And what we get here is 10,000 volts per meter. It seems pretty high, right? 10,000 volts given every meter, okay? That's our result. Okay, now, if you are uncomfortable or you were confused before as to why, if I zoom back out, as to why I got rid of this negative sign, right? Or I said, when I put the box around it, I said, again, if we don't care about the sign of this, because remember, potential is related to potential energy, in which case we get to set the zero of potential just like we did last semester. Okay, another way of saying that is that electric field is a vector, right? Its sign is determined by something. Its sign here is determined by the fact that it points in the direction of decreasing potential. So I got a positive value here with the way that I plugged in delta V. But my answer is still supposed to be to the left. Okay, so one way for me to do it is do it exactly how I did it here. Another way for you to do it is to just, maybe you chose 100 volts minus 200 volts, in which case you got a negative. But then you want to make sure that that negative means that you're moving to the left, right? We don't want to double count anything, okay? Again, this is meant to be, there is a little bit of arbitrariness there, but what we care about is there's a potential difference, and whether we call it A to B to B to A, is, we're going to see as time goes on, is really going to be, for the most part, irrelevant, okay? Let's kick that up to about just as hard as I can make this sort of problem, right? Same concept, but adding in something that makes it look like, well, now it's not so perpendicular anymore. Okay. Let's say that we have the electric potential at point A is negative 300 volts. What is the potential at point B, which is 5 centimeters to the right of A? Okay, so I'm just going to zoom this in a little bit, and I'm just going to pencil that in so that we know that this distance here, I'll call it X, is 5 centimeters. Okay, now notice there's this weird 30-degree angle that the electric field is going at, right? What do we know about the direction of the electric field? It always points in the direction of decreasing voltage, and it's always perpendicular to equipotential lines. So why don't we pencil in where the equipotential lines are? The equipotential lines are definitely not going to be here and here like they were in the last problem, because then the electric field, as given, would not be perpendicular. So let's get rid of those. What is perpendicular? What is perpendicular to those lines? Well, do we all agree that if the equipotential surface went like this, then yeah, we can see that these lines here are definitely coming out perpendicular to it. Yes, I'm doing my best to draw that as best as possible, which means everywhere along this purple line here, the potential along that line is negative 300 volts. Everywhere along this line, there's some other potential, the potential at B, that we don't know. What do we know though? We definitely know, as a gut check, the potential at B has, the potential at B has got to be less than the potential at A. And how do we know that? Because if the lines are pointing to in that direction, then it has to, the electric field has to be perpendicular to the equipotential surface and pointing in the direction of decreasing potential. So this has got to be something less than negative 300 volts, like negative 400 volts or something like this, okay? Or maybe even greater. And we know this formula is true, right? We know that the electric field times some distance is equal to the change in potential. But again, what distance are we talking about here, right? We're talking about a distance that is perpendicular, or that goes along with the potentials. Namely, we're talking about this distance here, but what we have is, we have this distance, yes? But notice all is saved because this makes a right triangle. This that I'm putting in green is the distance d that we want. And now I'll zoom that back out. So d here is going to be adjacent to that angle 30. So this is going to be our 5 centimeters times the cosine of 30. And then we are good to go because E times that D is going to be equal to the change in potential, right? Where did we start this, right? We started this at point A and then we end up at point B. So this is E times X cosine 30, because X was given, remember, as 5 centimeters, is equal to the potential at A minus the potential at B. Put a check mark next to what we know and underline what we don't. We know the electric field is 1200 volts per meter. We know X, we know cosine 30, we know the potential at A, so we can solve this for the potential at B. And so the potential at B then is going to be the potential at A minus EX cosine 30. And when I plug this into my calculator, notice that potential A is going to be negative minus another negative. It's going to be an even more negative number. This is going to be negative 352 volts, which we see is definitely less than the potential at A, which was one of the things that we anticipated. So this actually works, okay? Just to convince you that we could have got here in another way by using what we did last semester, let's just do it another way, right? If we take this and do it again, instead of using this new formula, if we do it in terms of the work that it would take to go across that potential difference, then we know that the work is equal to the force multiplied by some distance, right? Again, now the force has to be in the direction of the distance, right? That's our good old dot product, right? Which we know if the electric field points at this direction, then the force points in the same direction as the electric field, which means then we're right back to where we were up here, that the piece of that is parallel has got to be that diagonal purple line that we could label with the green D there. Okay, and so what we see is that, again, plugging in the fact that force is Q times E for whatever charge in question. I didn't give us a charge, but we'll see that's going to be okay, right? This is going to be Q E X cosine theta. And again, just like we did last semester, right? This is going to be equal to the negative change in potential. Once again, we know that the relationship between potential energy and electric potential is the charge that we're talking about multiplied by the potential. So QEX cosine theta is equal to the negative Q V final minus V initial, which again then becomes QEX cosine theta is equal to negative Q V final plus Q V initial. There's a Q with everything, which is great because we didn't know it anyway. And so what do you know here? V final is the potential at B. V initial is the potential at A. And so if we plug this in then and solve for the potential at point B, which is what we wanted above, the potential at B then is equal to potential at A minus EX cosine theta, just like we had before. Either way we get there, I mean, this is how physics works, right? It's always got to give us the same thing. So again, now we've seen a couple of different types of problems with potential and potential energy, right? There's just, you know, two-player systems, one-player systems, potential energy versus potential. Then there's the idea that, well, in those two-player or one-player systems, we could talk about the bonds or potential bonds that you would have. We can also not just calculate it from our KQ over R or KQQ over R for the potential energy. We can not also just calculate it. We could also then use conservation of energy, right, to say how things move. And we did problems like that in the previous video. But now we have a way to show how potential difference, the difference between two places potential, is related to electric field. And what do we see? If we have a potential that's something over here and something else over there, there's going to be an electric field there. And again, the key there that we need to take away conceptually is that a difference of potential means that an electric field is flowing. If an electric field is flowing, that means that there's force. So if you put charges in there, they're gonna move. This is how we move charges, by creating potential differences. And this is exactly what all those batteries that you've been using your entire life do. They hold a voltage, which means they create a potential difference between 2 points. They have stored energy, potential energy, which then allows them to build an electric field, create force, and carry charges away with it. Okay, ladies and gentlemen, in the next video, we will talk about what those things are that we can make with these. But when we come back to class, we're gonna do lots more problem solving, so let's make sure that we're all with it. And I look forward to seeing you all again very, very shortly. If you have any questions, comments, complaints, or concerns, as always, please don't hesitate to ask, and I hope that you have a fantastic weekend.